The singularity at the heart of a black hole is one of the most perplexing concepts in astrophysics. It represents a point of infinite density where the gravitational pull is so strong that space and time collapse into one another. At this core, known physics as described by general relativity fails to provide answers, as the equations result in infinities that defy logical interpretation. This breakdown highlights a significant gap in our understanding of the universe and prompts scientists to search for a theory that merges general relativity with quantum mechanics. In the singularity, the fabric of space-time itself is so severely warped that conventional ideas of distance, direction, and the flow of time lose their meaning. General relativity describes how massive objects warp space-time, but it cannot explain what occurs when this curvature becomes infinite. This has led to the idea that quantum gravity, a yet-to-be-formulated theory combining quantum mechanics and general relativity, could provide the tools to understand the behavior of matter and energy at this level of density. Quantum mechanics, which describes the behavior of particles on the smallest scales, contradicts the deterministic nature of general relativity. While general relativity deals with the curvature of space-time caused by massive objects, quantum mechanics deals with the probabilistic nature of subatomic particles. The singularity of a black hole represents a place where these two frameworks collide, exposing their limitations and the need for a unified theory that can handle extreme conditions. One proposed theory to bridge this gap is loop quantum gravity, which attempts to quantize space-time itself, suggesting that space-time has a discrete structure at the smallest scales. Another is string theory, which posits that particles are one-dimensional strings and that different vibrational states create the fundamental forces of nature. Both approaches aim to prevent the formation of a true singularity by introducing mechanisms that counteract infinite density. The event horizon surrounding the singularity complicates our ability to study what lies within. Anything crossing this boundary is hidden from the outside world, including light and information. This raises the question of what happens to the information carried by particles that fall into a black hole. According to classical understanding, this information is lost forever, which violates the principles of quantum mechanics. This apparent contradiction is known as the black hole information paradox and is one of the greatest challenges in modern theoretical physics. One hypothesis to resolve the information paradox is that black holes could retain or emit information through quantum processes. Theoretical physicist Stephen Hawking introduced the idea of Hawking radiation, where quantum fluctuations near the event horizon allow black holes to emit radiation and gradually lose mass over time. This process suggests that black holes could eventually evaporate, releasing the information they contain in a scrambled form, though this remains highly debated. The nature of the singularity poses deep philosophical and scientific questions about the universe's fundamental structure. If space-time can reach a point where traditional physics breaks down, what does that mean for our understanding of reality? The singularity could be a window into understanding how the Big Bang began, as the universe itself started from an extremely dense state where space and time were similarly intertwined. Theoretical models exploring the interior of black holes also include concepts such as spaghettification, where intense gravitational gradients stretch and compress objects falling toward the singularity. This tidal force becomes so extreme near the center that any object, including particles and light, would be pulled apart to an unrecognizable degree. Despite the dramatic nature of these forces, they offer a glimpse into the raw power of gravity and its influence on matter. The singularity's enigma continues to inspire new research aimed at reconciling our most successful physical theories. Efforts to develop a theory of quantum gravity could not only reveal the true nature of black holes, but also lead to revolutionary insights about space-time and the universe as a whole. Until then, what lies within the singularity remains one of the greatest unsolved mysteries in science, embodying the limits of current knowledge and the promise of future discovery.
Black holes, often perceived as cosmic monsters, play a surprisingly constructive role in shaping the universe. At the heart of most galaxies, including our Milky Way, lies a supermassive black hole that acts as a gravitational anchor. This central black hole helps hold the galaxy together, influencing the orbits of billions of stars and ensuring the stability of the galactic structure over billions of years. Without this anchoring force, galaxies might lack their characteristic shapes and dynamics. The gravitational pull of black holes extends far beyond their immediate vicinity, impacting the motion of stars and gas clouds throughout their host galaxies. This gravitational influence contributes to the formation of spiral arms and other galactic features. As stars orbit near black holes, they are subject to intense gravitational forces that can accelerate their speeds to extraordinary levels, creating fascinating phenomena like hypervelocity stars. Black holes also regulate the flow of matter and energy in their surroundings. As they consume gas and dust, they emit powerful jets of particles and radiation that travel vast distances. These jets, produced by supermassive black holes at the centers of active galaxies, can heat intergalactic gas and prevent it from cooling and condensing into new stars. This feedback mechanism plays a key role in galaxy evolution, balancing star formation rates and shaping the distribution of matter. Quasars, among the brightest objects in the universe, owe their incredible luminosity to black holes. These phenomena occur when supermassive black holes accrete large amounts of matter, creating an intensely hot accretion disk that emits radiation across the electromagnetic spectrum. Quasars can outshine entire galaxies, serving as beacons that illuminate distant regions of the universe and provide insights into the conditions of the early cosmos. In addition to shaping galaxies, black holes act as laboratories for studying the most extreme physical conditions. The immense gravitational forces near their event horizons stretch and compress matter in ways that cannot be replicated elsewhere. This provides unique opportunities for scientists to test theories of gravity, quantum mechanics, and high-energy astrophysics. Observations of black holes allow researchers to explore the fundamental laws governing the universe. Black holes also play a role in the formation and evolution of star clusters. Stellar black holes, formed from collapsing stars, can influence the dynamics of nearby stars, creating dense stellar environments. These interactions can lead to phenomena such as the merging of stars and the creation of gravitational waves, which ripple through spacetime and carry information about cosmic events. Gravitational wave astronomy has opened a new window for studying black holes, particularly through the detection of black hole mergers. When two black holes collide, they release enormous amounts of energy in the form of gravitational waves, providing direct evidence of their existence and offering insights into their properties. These observations have deepened our understanding of how black holes form, grow, and interact. Black holes also contribute to the recycling of cosmic material. As they consume matter, the resulting energy output can influence the distribution and composition of interstellar gas, enriching the environment for future star formation. This cyclical process underscores the interconnectedness of black holes and the broader processes that drive cosmic evolution. While black holes are often depicted as destructive, they are integral to the balance and order of the universe. Their gravitational influence, energy emissions, and interactions with matter contribute to the structure and behavior of galaxies and other cosmic systems. By studying black holes, scientists gain valuable insights into the mechanisms that govern the universe on the largest scales. The role of black holes extends beyond their immediate surroundings, highlighting their importance in the grand tapestry of the cosmos. They are not just endpoints of stellar evolution or regions of spacetime distortion, but dynamic and influential components of the universe. Their dual nature as both destroyers and creators exemplifies the complex interplay of forces that shape existence.
Observing black holes directly is impossible because no light or information can escape from within their event horizons. However, their existence can be inferred through indirect evidence and the effects they have on their surroundings. One of the most telling signs of a black hole is the behavior of matter and light near it, which reveals the immense gravitational influence of these mysterious objects. When matter falls toward a black hole, it forms an accretion disk due to its angular momentum. This disk consists of gas, dust, and other material spiraling at high speeds as it approaches the event horizon. The friction and gravitational forces within the disk heat the matter to extreme temperatures, causing it to emit radiation, particularly in the X-ray part of the spectrum. This emission provides a detectable signal that astronomers can study to locate and analyze black holes. X-ray telescopes, such as NASA's Chandra X-ray Observatory, have been instrumental in identifying black holes by detecting high-energy radiation from accretion disks. In binary star systems, a black hole can accrete matter from a companion star, creating intense bursts of X-rays. These systems, known as X-ray binaries, offer compelling evidence of the presence of stellar mass black holes. In 2019, the Event Horizon Telescope (EHT) provided a groundbreaking moment in the study of black holes by capturing the first-ever image of a black hole's shadow. This image showed the silhouette of the event horizon surrounded by a glowing ring of plasma, which is the hot, energized matter orbiting near the black hole. This historic achievement confirmed theoretical predictions and offered direct visual evidence of a supermassive black hole. The black hole imaged by the EHT resides at the center of the galaxy M87 and has a mass equivalent to billions of suns. The image highlighted the bending of light around the event horizon, a phenomenon known as gravitational lensing. This bending creates the shadow effect, which corresponds to the region where light cannot escape due to the intense gravitational pull. Another way black holes reveal their presence is through their gravitational influence on nearby stars and gas clouds. In regions like the center of our Milky Way, astronomers have observed stars orbiting an invisible object with incredible speed. These observations led to the discovery of Sagittarius A*, a supermassive black hole at the heart of our galaxy. Its mass has been calculated based on the motion of surrounding stars, providing further confirmation of its existence. Gravitational waves, ripples in spacetime caused by the acceleration of massive objects, have also become a vital tool in observing black holes. Detected for the first time in 2015 by the LIGO and Virgo observatories, these waves were generated by the merger of two black holes. The observation marked a new era in astrophysics, allowing scientists to study black holes through the distortions they create in spacetime. The study of black hole mergers continues to provide valuable insights. Gravitational waves carry information about the masses, spins, and distances of merging black holes, helping researchers understand their formation and growth. These observations also confirm theoretical predictions about the behavior of black holes in extreme environments. Observing black holes indirectly has deepened our understanding of their role in the universe. The high-energy phenomena associated with accretion disks, the detection of gravitational waves, and the movements of nearby stars all serve as tools to study these enigmatic objects. Each method complements the others, building a comprehensive picture of black holes' nature and influence. Despite their elusive nature, black holes have become some of the most studied objects in the universe. The combination of observational techniques and theoretical models has transformed our understanding of these cosmic phenomena. Ongoing advancements in technology promise even more detailed observations, potentially unlocking new secrets about the universe's most mysterious entities.
Black holes, despite their ominous reputation, are not inherently dangerous unless an object ventures too close to their event horizon. The event horizon marks the boundary beyond which escape is impossible due to the black hole's immense gravitational pull. Objects or particles that remain outside this boundary are not directly affected, making black holes less of a universal threat and more of a localized phenomenon. For Earth and its inhabitants, the likelihood of encountering a black hole is extremely low. The nearest known black hole, V616 Monocerotis, is about 3,000 light-years away, far too distant to have any effect on our planet. Even the supermassive black hole at the center of our galaxy, Sagittarius A*, is safely situated around 26,000 light-years away. Its gravitational influence, while significant in its immediate vicinity, does not extend far enough to impact our solar system. If a black hole were to pass closer to Earth, it could indeed cause catastrophic effects. Its gravitational forces would disrupt the orbits of planets, potentially ejecting them from the solar system or pulling them into its grasp. However, the universe is vast, and the chances of such an encounter are exceedingly slim, making it more of a hypothetical concern than an imminent danger. For an object to be consumed by a black hole, it must lose enough angular momentum to spiral inward toward the event horizon. Most objects in space, such as stars and gas clouds, maintain sufficient momentum to orbit black holes without falling in. This dynamic creates stable systems where black holes coexist with other celestial bodies without necessarily posing a threat to their neighbors. One reason black holes are often misunderstood as universally dangerous is their association with destructive phenomena like tidal forces and spaghettification. While it's true that objects approaching a black hole can be stretched and torn apart by extreme gravitational gradients, these effects occur only within close proximity to the event horizon. Farther away, the gravitational pull of a black hole is no different from that of any other object with the same mass. Black holes are not cosmic vacuum cleaners indiscriminately devouring everything in their path. In fact, many black holes exist in isolation, far removed from other matter. Even when they are part of binary systems or galactic centers, they interact with their surroundings in ways that can be studied and understood. This challenges the popular notion of black holes as uncontrollable forces of destruction. Earth's safety from black holes also stems from the stability of our solar system. The sun's gravitational dominance keeps planets, including Earth, in their orbits, and no black hole is close enough to disrupt this balance. Additionally, any black hole formed nearby would require a massive star to collapse, an event that would be observable and predictable long before it posed a risk. Hypothetical scenarios, such as the creation of microscopic black holes and particle accelerators, have been thoroughly analyzed by scientists. Studies have shown that these tiny black holes would evaporate almost instantaneously due to Hawking radiation, posing no threat to Earth or its inhabitants. Such scenarios remain theoretical and have not been observed in experiments. Black holes can even be beneficial in certain contexts. For example, their immense gravitational pull helps anchor galaxies and regulate the flow of matter and energy. Without supermassive black holes at their centers, galaxies might not maintain their structure over billions of years. This reveals the dual nature of black holes as both destructive and stabilizing forces in the universe. In the vastness of space, black holes are far more fascinating than dangerous. They provide unique opportunities to study extreme physics and explore the limits of our understanding of gravity and space-time. For Earth and humanity, black holes are more a subject of scientific curiosity than a cause for concern, emphasizing the balance between their dramatic nature and the reality of their limited reach.
The future of black hole research promises to deepen our understanding of these enigmatic cosmic entities. Advances in technology, particularly in telescopes and observatories, are enabling scientists to probe the universe with unprecedented precision. Gravitational wave detectors like LIGO and Virgo have already revolutionized the field by detecting ripples in space-time produced by black hole mergers, providing direct evidence of their existence and shedding light on their dynamic interactions. These detections have opened new avenues for studying black holes, including their masses, spins, and the environments in which they form. By analyzing gravitational wave signals, researchers can piece together the history of merging black holes, offering insights into their evolution and the role they play in shaping the cosmos. This new window into the universe complements traditional observational methods, creating a more complete picture of black hole behavior. Space-based observatories like the planned Laser Interferometer Space Antenna, LISA, are set to take gravitational wave research even further. Positioned in space to avoid Earth's seismic and atmospheric noise, LISA will be able to detect lower-frequency gravitational waves from supermassive black hole mergers and other cosmic phenomena. This will expand our understanding of how black holes interact on both stellar and galactic scales. Another frontier in black hole research involves imaging their event horizons and surrounding environments. The success of the Event Horizon Telescope in capturing the first-ever image of a black hole's shadow has spurred efforts to refine this technique. Future improvements in telescope arrays and imaging algorithms will provide even more detailed views of the environments around black holes, revealing how matter behaves under extreme gravitational forces. Theoretical advancements are also critical in exploring the mysteries of black holes. Efforts to reconcile general relativity with quantum mechanics are gaining momentum, as black holes represent a unique testing ground for these theories. Concepts like quantum gravity aim to explain the singularity at a black hole's core, where current physics breaks down. Progress in this area could revolutionize our understanding of the fundamental forces that govern the universe. One of the most intriguing questions in black hole research is the nature of the information paradox. As matter and energy fall into a black hole, the fate of the information they contain remains a subject of intense debate. Theoretical models, including Hawking radiation and holographic principles, suggest possible resolutions to this paradox, but definitive answers are still elusive. Future breakthroughs in quantum theory may help resolve this long-standing puzzle. The potential for black holes to serve as portals to other regions of space-time is another area of speculative research. While current evidence does not support the existence of traversable wormholes, black holes' extreme conditions challenge our understanding of space-time and raise questions about the possibility of exotic phenomena. Continued exploration of these ideas could lead to profound discoveries about the nature of reality. Artificial intelligence and machine learning are becoming valuable tools in black hole research. These technologies are helping astronomers analyze vast datasets from observatories and simulations, uncovering patterns and correlations that might otherwise go unnoticed. By automating complex calculations and modeling, AI is accelerating discoveries and generating new hypotheses about black hole behavior. International collaboration is key to advancing black hole research. Projects like the Event Horizon Telescope involve teams from around the world, pooling resources and expertise to tackle some of the universe's most challenging questions. This cooperative approach ensures that progress in black hole science benefits from diverse perspectives and the combined efforts of global research communities. As we continue to investigate black holes, their study not only enhances our knowledge of the universe but also challenges our understanding of fundamental physics and reality itself. They force us to confront the limits of our theories and inspire new ideas about how the universe works. The future of black hole research promises not just answers but also deeper questions that will keep humanity looking to the stars with curiosity and wonder.